Hello everyone, welcome to video lecture series of Design of Steel Structures. We are dealing with unit number 5th B part, Design of Welded Plate Girder. In the introductory lecture, we have seen what are plate girders, what are the cross-sectional components of welded plate girder, what are the functions and how the load transfer mechanism is taking place in case of plate girders. We have also seen the ratio for calculating your shear buckling strength, that is D by TW ratio, three types of ratio, and based on that only your numericals are classified. I have classified these particular three ratios as condition 1, condition 2 and condition 3, and according to that only we are going to observe three different numericals where your D by TW ratio or K ratio is initially less than or equal to 67 epsilon for condition 1. For condition 2 it will be between 100 to 200, and for condition 3 or third video it will be equal to greater than 200. Likewise, three videos we are going to cover according to conditions, and here the design steps for design of cross section, now secondary design of cross section and design of end bearing stiffeners, and third will be design of cross section, end bearing stiffener and intermediate stiffener with connection will be done. So when condition number 3 will be covered, so all the conditions and all the design steps related with girder will be covered. So we'll start with this particular numerical. So before that we will just check the overlook of design procedure for welded plate girder as per IS 800 2007. So initially you need to design maximum shear force and bending moment. Already for beam sections we have defined this and we have seen the standard conditions. When simply supported beam subjected to UDL, it is WL square by 8. Simply supported beam subjected to central point load, it is WL by 4, and simply supported beam subjected to eccentric load, it is WAB by L. So according to these conditions, or there may be combination of these conditions, you should be able to calculate the maximum shear force and bending moment initially, because based on this only your cross section will be defined. The next, initial size of plate girder. So first of all you design the web portion, then you go for design of flange plates and satisfy the cross sectional details by calculating design bending strength. So calculate the movement capacity of girder, then check the shear capacity of web, design of web connecting the flange plate, so design of connection between web and flange. Now design or requirement of EBS, that is end bearing stiffeners, design of web plate, design of weld between web plate and stiffeners, check for load bearing of stiffener, check for intermediate stiffeners, and last design of welded plate, weld between web plate and stiffener. So these are to be for procedure followed for design of your girders. We will directly switch towards the numerical. So this is the numerical statement. Design a welded plate girder of 24 meter span to carry superimposed load of 35 kilonewton per meter. Avoid use of bearing stiffeners and use Fe410 grade of steel for design. Assume suitable data if required. So in the numerical statement you can observe that it is a 24 meter span girder. You can observe the span. Up till now we were dealing with the numericals where span was up to 6 to 8 meters only. Here in case of this girder, the span is exactly 24 meters. So you can understand the amount of bending moment will be acting on the cross section. Again it is subjected to superimposed load of 35 kilonewton per meter. Uniformly distributed load is given, and again it is a working load or service load, it is not a factored load. So this particular given loading is to be multiplied with 1.5 partial safety factor in order to calculate the factored load. And they are again asking to avoid use of any kind of stiffeners, correct? So in short it will be condition number 1, and according to this statement or wording only you should be in position to define that D by TW ratio. So in the given statement you can observe that there is no requirement of stiffener, and when your requirement of stiffener is not there means your web is itself having greater capacity to take the load. Therefore it will be coming under first ratio, that is D by TW less than or equal to 67 epsilon. Material grade is given as Fe410. So here in this particular diagram you can observe uniformly distributed load, span, maximum shear force and maximum bending moment. But initially as it is a working load, it is to be multiplied with 1.5. Calculate factored load, Fu and Fy is given. So factored load is UDL, maximum bending moment will be W square by 8 and maximum shear force will be W into L by 2. Correct? So same values are calculated here. So after that you are requiring to take the self weight. So self weight is what? Self weight is total load. So total load is W into L. This is factored load into L span divided by 200. So we are getting 6.3 kilonewton per meter. Add this value to calculated factored load. You will be getting 58.8. Now put this value here and calculate maximum bending moment, maximum shear force. So that values we are getting near about 705.6 kilonewton, and bending moment we are getting 4233.6 kilonewton meter. Now you can observe the value. Almost that value is greater than 4000 kilonewton meter. This much is the tremendous amount of movement acting on the cross section, and for this value now you can observe that your regular rolled sections are insufficient to carry this moment. If you consider example of ISWB 600, almost greater than 1500 or 1800 kilonewton meter is the capacity of that cross section, and almost here the load is acting is 4200 kilonewton meter. So for these cases only, or this situation is only making us to go for welded sections. Correct? So these are the, in first step you have calculated shear force 705 and bending moment 4233. Now initially depth of web plate, that is the first step, but before that three conditions or three d by dw ratios we have seen. If stiffeners are to be avoided, the value should be 67 to 100. First condition, if only end bearing stiffeners are to be provided, it should be 100 to 200, and if intermediate as well as end bearing are required, it should be 200 to 270. So likewise these are approximation values, you can adapt value in between this. So initially suppose for first conditions we are going to adapt your ratio or d by tw value. In case of first factor, that is exactly equal to suppose 67 epsilon. We'll go with first value only, that is d by tw as 67. So depth or economical depth is calculated as cube root of, economical depth is calculated as cube root of movement into k factor. Now k we are assuming as 67 for condition number 1, as no stiffeners are required, divided by fy. So putting the values you are getting 1042.99. So we are round figuring that value to 1050 mm. So I have round figured that value to 1050 mm. So depth of your web plate is 1050 mm. Now again we are having the ratio d by w, we have assumed as 67. You can calculate the thickness. So adapted depth divided by ratio 67, you will be getting the thickness now, that is equal to 16 mm. So you can define web plate size 1050 by 16 mm. Now here you can observe that instead of this particular 67, if you have adapted ratio 100 to 200, what would have happened? The thickness is somewhat lesser than 16. So as you are going to reduce the thickness, the tendency of buckling is going to increase. So same problem we are going to cover in condition number 2 also. Now next, area of flange required. Now web is designed, go for flange. Area of flange required. So area of flange required is, so value is given as AF into your stress Fy multiplied by depth divided by gamma m0, and that is to be equated with maximum bending moment. So rearranging the terms, you can calculate AF value, that is area of flanges, just by putting bending moment of maximum value 4233.6 into 10 raised to 6. Now the calculated value or area of flanges is equal to 17,741 mm square. So the flanges are to be required of this size, 17,741 mm square. Now importantly, your flange to be in plastic or semi-compact, flange to be in plastic or semi-compact, it is approximately defined, or it is approximately decided as 0.3 to 0.4 times of depth adapted. If you are adapting the width of flange in between 0.3 to 0.4 times of depth, the section is going to be, or the cross section is going to be in plastic shape or plastic classification, and that is important for our design. So we'll adapt, suppose the width of flange as 0.4 times of depth. So 0.4 times of your adapted depth value, we are getting 420, and I have round figure that value to 450 mm. Similarly, now area of flange is known to us, that is BF into TF. Area is known, width of flange you have defined as 450. Now you can calculate the thickness of flange, and I am getting thickness of flange as 39.42. Again I have round figure that value to 40. So likewise 450 into 40 is the size of flange, and web is 1050 by 16. So likewise your cross section of girder is defined. Two flange plates of 450 by 40 and one vertical web plate of 1050 by 16. So here you can understand that this is the cross section that we are adapting. Your flange portion is 450 by 40, 450 by 40, and web is 1050 by 16. So this is the cross section that we are adapting. Now just making the classification, BF by 2 divided by TF, we are getting 5.62 less than 9.4 epsilon, it is plastic. Similarly for D by TW, 1050 by 16 is less than 67 or 84 epsilon, it is a plastic. Therefore you can define the cross section is a plastic cross section. Now this same second check for classification is not going to satisfy for condition 2 and condition 3, because intentionally we are failing our web for economy. So same portion will cover in condition number 2 or next video. So now calculating the moment of inertia, now you can observe that the section is symmetrical about both the axes, but adapting your parallel axis theorem, there will be parallel axis for this particular horizontal side or z side. So adapting Ig plus Ah square. So initially your moment of inertia for rectangular section BD cube by 12 into area into h square. So h value is going to be 1050 by 2 plus 40 by 2. So that value is 545 square, and for vertical portion it is 16 into 1050 cube by 12. So I am getting something around 1.22 into 10 raised to 10 mm raised to 4. Similarly along y side there is no parallel axis along y side, therefore it will be only Ig value, so that is dV cube by 12. So calculating that I am getting 607.85 into 10 raised to 6 mm raised to 4. Now what will be the extreme fiber distance from bottom and top? It is nothing but overall depth divided by 2. So 1130 divided by 2 is nothing but I am getting 565 mm. As it is symmetrical, exactly your extreme fiber, compression fiber or your tension fiber is at a distance of 1130 divided by 2. So that is 565. Now based on this only you can calculate the elastic section modulus. Elastic section modulus is nothing but it is moment of inertia divided by extreme fiber distance, either bottom or top. So as the symmetrical section, bottom and top is the same value, therefore along z side I am calculating. So elastic section modulus along z side, so Izz divided by Yb or Yt, so I am getting 21.66 into 10 raised to 6 mm cube. Now this is elastic section modulus, and for design you are requiring plastic section modulus. So plastic section modulus can be either calculated using parallel axis theorem, parallel axis, or it may be equal area axis, or it may be calculated directly as it is a rectangular section using shape factor. So for rectangular section shape factor is near about 1.14. So calculated value into 1.14, you are getting 24.69 into 10 raised to 6 mm cube as your plastic section modulus. Now how we are defining or how we are designing the design bending strength in case of laterally supported type of beams, it is beta b into plastic section modulus into Fy divided by gamma m0. So already we have done this for flexural members in unit number 4, just putting the value of beta b as 1, plastic section modulus as calculated 24.69 into 10 raised to 6, Fy is 250 and gamma m0 is 1.10. You are getting the capacity of girder as 5103.11 kilonewton meter, and you can observe this is almost greater than our requirement of 4233.6 kilonewton meter. So in short, the selected cross section is satisfying our condition. The capacity of section is greater and the amount which is going to act on the cross section is lesser, that is 4233.6 kilonewton meter. So our cross section is satisfying. Now next is shear strength capacity of section. Shear strength capacity of section. So shear strength capacity is calculated for regular beam. Likewise your regular beam only, Vd value, and Vd is given as shear area into Fy divided by root of 3 into gamma m0. So shear area now here will be exact depth of web into thickness of web, which was previously considered as overall depth into thickness of web, because that was for rolled section, and here we are adapting a built up section. Now shear area is exactly 1050 into 16 only up to this value. So putting that value here, you are getting shear capacity as 2200 kilonewton, and our shear force was only 705. So again it is greater. Again calculate 0.6 VD value. So 0.6 value is 1322. Again it is greater than maximum shear force 705. So it is a low shear condition, and our assumption of MD calculation is correct. Now directly we will go for check for web buckling. So same calculation this we have performed for your beams. So web buckling FW is area effective into FCD. Area effective is width of bearing into thickness into FCD value. So we'll assume that width of bearing plate is 150 mm, and single dispersion it will be equal to 150 plus d by 2. So 150 plus total depth divided by 2 is we are getting 715 mm, and thickness of web is 16 mm. Now FCD depends upon your lambda value KL by R. Now for KL by R calculation, initially R is to be calculated, and R value is under root of I by A. R value is under root of I by A. So just calculating that values, in case of your web portion we are considering, so it will be equal to web portion is web portion considering your width of bearing plate. So width of bearing plate here is 150 mm. Width of bearing plate is 150 into thickness is 16. So we are calculating moment of inertia for that width only. So it will be under root of 150 into 16 cube by 12, that is A value, and area will be 150 into 16. So I am getting your radius of gyration directly value as 4.61. Radius of gyration as 4.61. Just I have made here correction. I value it should be R value here instead of I. So direct answer I am getting 4.61, and always KL value is 0.7 times of depth. So 0.7 into 1050, it is 735 mm. So putting the values and calculating lambda, 159.43 almost equal to 160. So table number 9C for FY 250 FCD is 53.3 MPa. So 53.3 MPa into 16 into 715. Same calculation we are doing, and that is almost equal to 609.75 kilonewton. 609.75 kilonewton. But here it is failing for your buckling strength, that is 705.6 kilonewton. Fails in web buckling, therefore end bearing stiffeners are required. So either you may increase the bearing value, that is instead of 150 you may adapt this value as 200, or in second case you may provide end bearing stiffeners at both the sides. So both are the conditions, you may provide anything. So for example, the load carried by your bearing is near about 609, and the remaining force will be 705 minus 609, 95.85 kilonewton. So 95.85 value, for this value you need to design your end bearing stiffeners. So what is the width of stiffeners adapted or outstand of stiffener possible? If total flange width is 450 minus thickness of web divided by 2, so this is the maximum possible outstand possible for your stiffener, and that is equal to 217 mm. So you can provide near about 215 by 12 mm flat section as a stiffener on both sides. So on both sides we are adapting that, and this particular core area you can observe, these are your end bearing stiffener and this is your core area, and outstand we are adapting for the stiffener is 215 by 12 mm. Either you may take thickness of web equal to thickness of stiffener, or shortly you can vary that. So this core section is going to be 20 times TQ on both the sides, so 2 times 20 TQ. So outstand should not be greater than 20 TQ. So 20 TQ value, if 12 mm is the thickness, is 240, and minimum outstand is 14 TQ. 14 into 12, 168. So our value should be between 168 and 240, and we are adapting exactly 215, therefore it is okay. So effective area for this calculation, now it can be calculated 215 into 12 into 2 plus 2 into 20 into 12, 2 into 20 into 12. So again, yes, 2 into 20 into 12 into 16. So this core area, therefore 16 is multiplied because thickness of wave is 16. And similarly for this only you calculate moment of inertia. So again, parallel axis, distance between the two parallel axes, it will be 215 by 2 plus TW by 2, that is 16 by 2. So that will be equal to the value 115.5 square. So moment of inertia I am getting 88.87 into 10 raised to 6. Now similarly calculate R, radius of gyration, calculated moment of inertia divided by area under root value. 83.19. Same calculation, KL by R, 0.7 into 1050 divided by calculated radius of gyration, you are getting 8.83. So almost it is equal to 10 value, because in table value starts with 10. So calculate FCD for this 10 value, and that is equal to 227 MPa. Multiply this value with area, you are getting force near about 2914.68 kilonewton. So you can observe the tremendous increment in the shear capacity if the stiffener is provided. So almost it is equal to 3000 kilonewton if the stiffener of 215 by 12 is used. Now here you can observe that the girder is safe for carrying your shear force at supports or at your end bearing stiffeners. Next, check for web crippling, area effective into Fy divided by gamma m0. So area effective is B1 into Tw, and B1 depends upon 2 times thickness of flange plus R1, but R1 value is absent here, or it is not there, or it is neglected as it is directly your square section. R1 is there in case of your rolled section. So putting that values, B1 150 we have assumed, N1 is 2.5 times of thickness of flange is 40. So we are getting your crippling strength equals to 909 kilonewton, and it is greater than 705. Therefore for this condition also it is safe. Then last step is there, design of connection between flange and web. Flange and web is to be designed. So shear force is equal to 705.6 kilonewton. This is the maximum shear force for the cross section. So this was the cross section. So you need to go for design at this particular junction. So shear stress is to be calculated as this junction, shear stress at this junction. Already at some principle you have adapted for calculation of shear stresses, that is SA y bar divided by IB, but for rectangular section IB is 2 times moment of inertia. So same values are considered here. SA y bar divided by 2 times IZ. So S is maximum shear force 705, area above the junction, that is 450 into 40. Above the junction area is 450 into 40, and y bar is 545 divided by 2 times of moment of inertia. So near about we are getting 0.283 kilonewton per mm. 0.283 kilonewton per mm. This is the amount of shear stress occurring exactly at the junction of web and flange. So our welding should satisfy or should have strength greater than 0.283. If the adapted welding will be having strength greater than this value, then it will be safe. So for example, we will adapt size of welding. So size of welding depends upon thickness of thicker part to be connected, and we are having 16 mm square edge. Therefore we will adapt the size of thickness as 5 mm. We will go with size of welding 5 mm. So throat thickness will be 0.7 times of 5 mm. So that is equal to 3.5 mm. Now just calculate length of welding, or just calculate strength of welding per mm. If 1 mm length of welding is provided, what will be the strength? So strength of welding is provided. Strength of welding is calculated as length of welding into throat thickness into Fu divided by root of 3 into gamma mw. So yeah, gamma mw will be your fabrication, and for fabrication on shop fabrication it is 1.25. So putting the value, length of welding as 1 mm, length of welding is 1 mm, then throat thickness 3.5, ultimate strength 410 root of 3, and gamma mw 1.25. We are getting strength at 0.662 kilonewton per meter. So if 1 mm welding of size 5 mm is provided, it is having capacity to take 0.66 kilonewton load, 0.66 kilonewton load, and here you can observe that this is greater than 0.283. Correct? Therefore the cross section or the welding adapted is safe. Now instead of going for welding to be provided throughout the span, here you can observe that likewise intermittent welding may be provided. So instead of providing welding throughout the span, it may be provided at certain distance, and for that you are adapting clauses from connections IS 800. So the intermittent welding should not be less than 4 times size of welding or 40. So 4 into yes we are adapting 5, so it will 4 into 5, it is 20 mm or not less than 40. So 40 mm is to be adapted, and spacing should not be greater than 12 times thickness of your thickness of your girder section or web section. So 12 into 16 I am getting 192. So spacing should not be greater than 192. So in short I will define Size of welding 5 mm, intermittent welding at a length of 40 mm and spaced at a distance of 175 mm. So here in this particular figure you can observe that this particular welding length is 40 mm and again spacing between two welding is 175 mm. So this is cross section. These are the coping provided for your stiffeners. This is side elevation and this is your top view or top elevation, where stiffeners are provided only at the ends. Both the stiffeners are provided only at the ends because maximum force is acting as a shear force or reaction exactly as support, and for center span your shear force is going to be lesser value or zero value. Therefore there is no requirement of stiffener at center span. Usually in case of condition 2 we will observe that there may be requirement of stiffener at center span also if concentrated loads are there, and for condition 3 there will be requirement of stiffener along the span or throughout the span, but only they are provided in alternate fashion. So likewise your numerical is completed. Here we have just seen condition number 1 and adapting d by tw ratio or d by tw ratio as first condition, that is 67 epsilon. So here the numerical is completed. For your examination there may be similar kind of numerical, just there will be change in your loading mention. So we'll continue in the next video with condition number 2, adapting d by tw between say 100 to 200 value. Thank you very much.